In this image, you'll see a galvanic or voltaic cell. On the left side is the anode and the right side is the cathode. If you don't know what a voltaic cell is, I highly recommend you watching the video that's titled Galvanic Voltaic Cell. Now, moving on. Now, here is zinc, and the zinc will strip away its electron, and the electron will flow through this electrical wire, and then it goes into the cathode. So I'm going to go ahead and draw the electrons just flowing through this wire, and it's going towards the cathode side. At the cathode side, the electrons are picked up by the copper 2+, and then it's forming into copper solid. Now, as this electron is flowing through, it's going to flow through this little box called voltmeter. The voltmeter actually measures out how much this electron is flowing through, and it's going to measure the flow of the electrons, okay? And that flow of the electrons as it's passing through is going to be measured in a value, and this one happens to be 1.10 volt. Now you see this little symbol E0 cell. E0 cell refers to the standard cell potential. So what is standard cell potential? It is the voltage of the voltaic cell when the reactant and the product are in the standard state. In the standard state will be like 1 atm pressure, 1 molarity for these solutions over here, zinc sulfate and copper sulfate solution, and it's at 25 degrees Celsius. So that E0 cell is a symbol for the standard cell potential. So as the electron is flowing through in this direction, it's going to read 1.10. But say you didn't know that it's going to be 1.10. How do we calculate and how can we find out that there is this 1.10 that's going to occur? And yes, we can calculate out the standard cell potentials without actually going through this entire device. And so it is dependent, the cell potential is dependent on 2 of the half reaction that make up a cell. So let's find out the half reaction for these. Half reaction, say for, I'm going to go for the anode first, where zinc solid is forming into zinc 2+ aqueous, and it's going to lose 2 electrons. How did I know that? If I look at the oxidation number, zinc is 0 and zinc 2+ is +2. So therefore you need 2 electrons that needs to be taken out in order to become 2+, so hence 2 electron is on the right hand side. For the cathode side, we have copper 2+ in aqueous. I'm going to go ahead and add 2 electrons in and forming into copper solid. And how did I know that? Well, oxidation number for copper 2+ is +2 and copper is just 0. And so you needed to add 2 electrons in order from going from +2 and 0. Now, after you have figured out the half reaction, what you're going to do is you're going to find the E0 for each of the half reaction. You're going to find the standard cell potential for each of the half reaction. So where do I go to find this? You're going to look in the reference sheet, and in your reference sheet, you should find something that looks like this. Okay, so in this table over here, it says standard potentials at 25 degrees. All of the electrons you'll notice in this half reaction are on the left-hand side. So it's as if they're going through, all of these are going through reduction process. So one of the reaction in the previous, let me go back. Here you could see that there's a reduction going from copper 2+ to copper. So let's find what the standard potential value is for that. So copper 2+, I'm going to find it here. Right here. So here's my copper 2+ plus 2 electrons forming into copper. And the voltage here is 0.34 volt. So let's go back, and then I'm going to write 0.34. So this is 0.34 volts. What about for zinc? Now zinc this is going through oxidation process, but that entire list that you have seen before, that's not going through oxidation process, but it's going through reduction process. So if you look over here, zinc, added 2 electrons forming into zinc. This is a reduction process. So if it was an oxidation process, it would go to the reverse. Since the reduction process is negative 0.76, that means the oxidation process would be the positive of the negative 0.76. So instead of writing negative 0.6, you're going to write positive 0.76. So positive 0.76 volts. After you have gotten all of the E potential for all of these guys, I'm going to separate it. You're just going to add the 2. So if you add the 2 together, then you would get 1.10 volts. This will tell you the cell potential, the standard cell potential for this particular cell. And what do you know? The cell potential is 1.10 volts based on the experimental value. And then if you calculate it out, it will come out to be approximately the same. Let's do a learning check. We're going to go ahead and calculate the standard potential of the galvanics shown in this image. You will be utilizing the reference sheet, and you'll be utilizing in particular the standard half cell potentials table in order to solve this problem. In the left-hand side is the anode. This is where oxidation is happening. Oxidation reaction where copper 2 plus, so I'll write that down, copper 2 plus, is being formed from the copper solid. How did I know that? Well, if you look in this image here, it's showing that the copper solid here in this plate is forming into copper 2 plus. During this process in the anode, electron has been lost. Well, how much? Oxidation number for copper is 0, copper 2 plus is plus 2. That means that 2 electron has been taken out in order for the copper solid to become a copper 2 plus. And that's occurring in the anode. Let's talk about the cathode. In the cathode, we have silver plus. So we have silver plus, and that's from the aqueous forming into silver solid. And it's shown based on the image over here. And always on the cathode side, there is a reduction occurring. So they're going to be adding electron. Well, how many electrons? In the oxidation number for silver is silver plus 1 is plus 1. Silver solid is 0. So therefore, you only needed 1 electron to allow that silver plus to become silver. You'll notice also that this electron here is 2, whereas the electron over here is 1. We need to balance this equation so that there is a 2 to 2, meaning that there is, if 2 electrons are donated or taken out, then 2 electrons are accepted. So therefore, in the cathode side, I can multiply everything by 2. Multiplying everything by 2, then if I were to rewrite this, it becomes 2 silver plus 2 electrons forming into 2 AgS. Now we still haven't calculated the standard potential yet. We haven't even looked at it. So let's go ahead and look at that. So we're going to look at the standard cell for each of these half reactions. So we're going to look for copper, that forming into copper 2 plus, and silver forming into silver. Take out your reference sheet. This will be handy. So in this reference sheet, it's going to show the standard cell voltages if they were to go through reduction process. None of these are in oxidation process. But our half cell, well, one had oxidation process and the other one reduction process. So let's look at copper, the one that went into oxidation process. Here if it were to go reduction, there is copper 2 plus with 2 electron forming copper. The potential for this, the standard potential, is at 0.34 volts. If this were to go in an oxidation process, then this becomes not positive 0.34, but it's the opposite value, which is negative 0.34. For silver, however, this is showing the reduction process, and in our galvanic cell, this silver is going through reduction process, and the process is 0.80 voltage. Let's take both of those values and then place them into our PowerPoint. So for copper, it's not negative, it's not positive 0.34, but rather negative 3.34 volts. For silver, it was 0.80 volts. Although you may have multiplied this by 2, do not multiply this by 2. Now that we have the two voltages together, you're going to go ahead and add the two values. So negative 0.34 plus the 0.80. That would be 0.46 volts. So what is the standard potential of the galvanic shown below? It's this right here. And in order to do that, we need to find out the half potential for each. Let's do another learning check. Here it says, what is the standard potential for the following redox reaction? So instead of giving an image of a cell, it's giving you an overall reaction. We want to take half reactions and then go from there. Let's take chromate, so CRS forming into Cr plus 2. Well, this is probably going to be your oxidation process, or if it was in the cell, it would be in the anode. The oxidation number for chromate is chromium is 0, and for chromium 2 plus is plus 2. That means 2 electron has been taken out. What about for the other one, the silver? So we have silver plus, and we know from the previous learning check, you just needed 1 electron to form into silver solid. And this is a reduction process and happening in the cathode. Okay, so now it wants to know potential. Well, potential for each of these, go back to your reference sheet and check what those are, add the two values, and come back and check this video. And so here is the key.